Have you ever looked at a super complex puzzle, maybe a Sudoku or a massive scheduling problem, and just wondered how an AI cracks it? The first thing that probably comes to mind is just raw power, right? Trying trillions of combinations in a split second. But the real secret, the truly clever part, isn't about speed. It's about thinking like a detective, using pure logic to cross off all the dead ends before the real search even starts. So here's how we're going to break it down. We'll start with what makes these puzzles so tough. Then we'll look at two ways to solve them, the brute force way, and then a much smarter way using inference. We'll dive deep into how that smarter method works, see why it's such a game changer for huge problems, and then look at what this all means for the future of AI reasoning. So really, how does a computer stare down a problem with millions, maybe billions of possibilities and find the one right answer? Well, the very first step is to frame the problem in a way a computer can understand, with a clear, logical set of rules. Okay, let's make this real with a classic example, map coloring. You've got this map of Australia and just 3 colors to work with, let's say red, green, and blue. The rule is dead simple. If 2 territories share a border, they can't be the same color. So where do you even start? How would you solve this without just guessing randomly? This kind of puzzle actually has a name in computer science. It's called a constraint satisfaction problem, or CSP for short. And every CSP has 3 key ingredients. First, you've got your variables. For us, that's each of the Australian regions. Then you have the domains. That's your list of options for each variable, so our 3 colors, red, green, and blue. And finally, the most important part, the constraints. These are the rules, like Western Australia's color cannot equal the Northern Territory's color. All right, so let's explore the most obvious way you might try to solve this. It's time to meet our first problem-solving character, the brute. The brute strategy is, well, exactly what it sounds like. Just try everything. Pick a color for the first region, a color for the second, a color for the third, and you just keep going. If you hit a point where you break a rule, you just back up 1 step and try the next color on the list. A really common way to do this is with something called backtracking search. It's this systematic guess, check, undo, try again process. And hey, it'll get you the answer, eventually. But as the problems get more and more complex, this whole approach just hits a massive brick wall. And just how big of a wall are we talking about? Well, let's take a game like chess. The number of possible sequences of moves is estimated to be around 35 to the power of 100. It's a number so big, it's hard to even wrap your head around. To try and put that in perspective, that number is bigger than the estimated number of atoms in the entire observable universe. So yeah, trying to brute force that isn't just slow, it's literally impossible. Clearly, we need more than just raw power. We need a smarter way. And this is where things get really cool. This brings us to our hero, the detective. Instead of just blindly charging ahead, the detective is all about inference, using pure logical deduction to start solving the case before a single guess is even made. Let's put these two side by side. You've got the brute, who's just stumbling around in the dark, trying every door until one opens. It only finds out it made a mistake after the fact. But the detective? Totally different game. It uses logic to figure out which doors are definitely locked from the very beginning, preventing mistakes before they can even happen. This whole approach has a formal name, Constraint Propagation. And this quote from our source material really nails it. It says it uses the constraints to reduce the number of legal values for a variable, which in turn can reduce the legal values for another variable. You see, it's like a logical domino effect that simplifies the whole puzzle as it goes. Okay, so how does this detective actually work its magic? Let's pop open the hood and look at a couple of the key tools in its toolkit. First up is a technique called arc consistency. Now that sounds pretty technical, but the idea is actually super intuitive. The AI just looks at pairs of things that are connected, an arc, like South Australia and its neighbor, Western Australia. For every color South Australia could be, it just checks, is there at least one legal color left for its neighbor? If a choice for one variable makes the other impossible to color, then that choice is thrown out right from the start. It's like a real detective clearing away all the junk evidence. Watch how this plays out. Let's say we tentatively color South Australia red. Boom. The AI immediately propagates that constraint. It looks at all of South Australia's neighbors and deduces that red is now completely off the table for all of them. Instantly, the list of possible colors for those other territories, their domains, gets smaller. Just like that, the puzzle becomes simpler, and we haven't even done any real searching yet. Now, building on that, there's another great technique called forward checking. It's a lot like art consistency, but it's used on the fly, during the search. So every single time the AI makes a choice, it immediately checks forward to see how that one decision affects the options for everything else down the line. And this is where you see the real genius of it. Imagine we've colored Western Australia red and Queensland green. Now we try coloring Victoria blue. A simple brute force searcher might just plow ahead, but an AI using forward checking, nope. It immediately looks at South Australia and sees, wait a minute, it's now touching a red, a green, and a blue territory. It has 0 colors left. The AI knows this entire path is a dead end and backtracks right away, saving a massive amount of wasted time. So what's the actual payoff here? I mean, all this clever deduction, is it worth it? Oh yeah. The difference it makes is staggering. Just take a look at this. For our simple Australia problem, just using these logic tricks at the very beginning can wipe out up to 87% of the entire search space. The problem shrinks from this huge, messy thing down to something much more manageable before the first real guess is even made. That's the power of thinking like a detective, not a brute. And this isn't just for coloring maps. CSPs are the hidden engine behind solving some incredibly important real-world puzzles. We're talking airline scheduling, managing factory workflows, creating university timetables, designing computer chips, and yeah, even your favorite Sudoku. They're all, at their core, problems about satisfying a whole bunch of constraints. Now, this kind of logical inference has been a cornerstone of AI for decades. But don't think for a second that it's a relic of the past. It's actually more relevant than ever because what this all shows is that the future of AI isn't just about getting faster computers. The real cutting edge is developing more and more sophisticated ways for AI to reason, to understand the deep structure of a problem. And that is exactly what's happening right now. As this quote explains, researchers are blending these classic logic-driven techniques with modern machine learning. The result is a hybrid AI that can not only solve a problem, but can actually learn from experience to make even smarter deductions next time, becoming more adaptive and intelligent as it goes. So let that sink in. We've seen how AI can use pure logic to shrink a problem that has more possibilities than atoms in the universe down into something solvable. As these reasoning skills get even more powerful, it poses an incredible question. What are the impossible problems of today, in science, in medicine, in logistics, that will become the simple, solvable puzzles of tomorrow?